No, no, it's fine.
Yes, that's Marcel. Hi, Marcel. How are you?
Hi, Mohammed. Fine.
Nice to see you again.
Nice to see you. We are joining from the same office, so one sound system should be enough.
Okay. Okay, great.
Yes, Marcel, Joaquin. Yeah, we have.
I spread a bit the link, but I spread it a bit late because I didn't know what's the policy regarding it. So let's see if other people.
Yeah, well, it will be recorded also, so if anyone's interested, it's gonna be in YouTube.
Yeah.
The link. Yeah.
I'm going to call the guys in my
So I'm interested is which the Romanian, the Astronomical Institute of the Romanian Academy, is it in the Bucharest or is it in Craiova? So Craiova
In Bucharest.
It's in Bucharest.
Yeah.
Is Craiova very distant, very far from it, or close?
I think 3 hours by car.
Okay.
It's
Yeah,
not so
we
far.
are mostly in Bucharest now, but formally Georgia will be at the University of Craiova officially, let's say.
Okay.
But he is continuing to collaborate with me. We will be mostly based in Bucharest.
Yes, yes. It's nice. I should visit. I've never been to Romania.
We should do a project to visit.
Exactly. Yeah.
Yeah. You also have David there, if I'm not wrong. Yes?
Yes, yes. Is he here? Was he in the office today? David? Yes. Okay, so it should be coming. Hopefully. Yeah. Yeah. Was David there in the office? Was David in the office?
Yeah.
Yeah, he's coming?
Yes,
Because he's the most closely related to this.
Yeah.
He wants only rocks, not rocks with tails.
Exactly. Yeah. Let's see if you can push him into this field.
Yeah.
Diffuse solar system. Well, it's not emission, it's reflection.
Yeah, the Morate.
Yeah, Morate, I forgot his name.
Yeah, I was assuming that was David who invited us.
No, because this is on comments, so I'm actually a both of them, right? Okay.
Is it through the calling thing?
No, this isn't. It's from my time at the IAC. I met Marcel. He's over there. We collaborated on trying to detect the extended tail of the comet. So my first paper in solar system physics.
Ya que no te sentaste ahí, no. ¿Están pegados? Ahí va.
Morata, you should be host.
I know that guy. Oh, can they hear me?
Yeah.
Yes. Ted. Hello, I'm Morate.
The fact that you know him is not a good start for him.
We shared some memories together.
Yeah.
Yeah.
Okay, so should we start, Jairo?
Yeah, go on.
Okay, so I'm really happy to introduce George Prodan. So right now he's at the Craiova University. He's a research assistant there. He just finished his master's degree at Padova, and before that he was in the University of Bucharest, and over there he collaborated with Marcel and the Astronomical Institute of the Romanian Academy on this paper that he's going to introduce today. So he got his undergraduate in 2021, and before that he was also active in astronomy, as in the Astronomical International Olympiad of Astronomy. He got second, he got the silver medal. So that's really a lot of work from a very young age. Great work, George. Okay, so this is a work. How I relate to this, because I'm working in galaxies, as you all maybe know, is that while I was in IAC, my office was just 2 rooms away from Marcel. And then while we were, randomly talking, we discovered that detecting diffuse emission is also important in the solar system. So, we done some. So with Marcel, we played with noise chisel on this galaxy, and now George will explain more about this nice word. So thanks a lot, George, for accepting this invitation, and you can go ahead to present the talk.
Okay, thank you for inviting me, and thank you for the kind introduction. So today we will be discussing about the Interstellar Comet 2I Borisov, and I'll present the results of the Pre-perihelion monitoring campaign. So the Interstellar Comet Borisov is the first interstellar comet known, and the second interstellar object after the asteroid Ammonia. It was discovered by the astronomer J.R. Borisov at the end of August in 2019 from the Crimean Observatory. This kind of objects helps us understanding and answer questions related to the exchange of materials between 2 different planetary systems, how these interstellar comets behave in the vicinity of the Sun, and if they are comparable to those from our solar system. First, let me introduce a bit of context. So at this discovery, 2I was located at the geocentric distance of 3 astronomical units. It had a hyperbolic orbit, so an open orbit with high centricity. We can see here that it was located somewhere between the constellations Gemini and Lynx. And here is the orbit and how it intersects with the orbits of the solar system planets. The orbit has the orbital parameters are typical for an interstellar object. So we have the excess of velocity, which is high, of 32 kilometers per second. We have a high inclination, and of course a high eccentricity. The perihelion happened on 8 December 2019, when the distance was minimal between the comet and the Sun of 2 astronomical units. So a debatable topic about Borisov is its origin. It was proposed by Eubanks that it's a stardust comet due to its low water abundance that originates from the Wolf dynamical stream. A dynamical stream is a group of stars that are moving almost together with respect to the center of the galaxy. In this plot, we have the galactocentric components, U and V. And we can see that if you plot the Borisov components, it matches with the group of stars from the Wolf stream. And here Eubanks compared with the velocities of other dynamical streams. Another proposal was that Borisov home system is the Ross stellar system. They found out this by checking with the Gaia data released to astrometry. And Baylor Jones et al. Determined that the closest encounter will be this stellar system. So both suggest that the home system is a star that is in the vicinity of the Sun due to the similar velocity. Hypothesis that is supported by other groups as well. So being such an interesting object, many groups studied its properties. And here I will enumerate some physical properties. Jewett et al. Performed high-resolution imaging, and they found out that the flare radius is about 200, 500 meters. Some groups implemented tail models based on Monte Carlo simulations, and they found out that the dust grains have radius between 10 and 100 micrometers. And also we can find dust particles that are smaller in the coma or around the nucleus. Based on the same models, they could estimate dust production rates. The results vary because of the use of different models or different assumptions. And the assumptions could be related to the size distribution of the dust grains or the density. And here we have an image retrieved by the Hubble Space Telescope. We can see the coma that is aligned with the solar velocity, and it's on the right side of the anti-velocity vector. So an overall analysis of the properties suggested that the comet is not so different from the solar system ones. In particular, the morphology of Borisov is similar to a specific solar system comet exhibiting similar activation processes. The spectroscopic measurements show that we can find the usual lines of cyano, ammonia, oxygen, iron, nickel, and similar abundances. And multiple studies confirm that the colors resemble the solar system colors of the comets. And we can see here in this plot retrieved from Leon et al. That Borisov is quite similar photometrically with long period comets, short period comets, with the trans-Neptunian object and centaurs. What's unusual about Borisov is that it exhibits an unusual high ratio of carbon monoxide with respect to water and hydrogen cyanide. And this can be explained because of the lack of water. There are no absorption bands of water ice. So this is an unusual thing. And the presence of forbidden oxygen lanes could mean that this is a good tracker for water. So we have here plotted the green and red lines, the ratio between the green and red lines fluxes, and we can see that for Borisov we have high ratio. However, this is not so much water in Borisov, and this high ratio is due to the carbon monoxide. And we have another comet, a single comet from the solar system that is also abundant in carbon monoxide. And we can see this particularity here. In addition, the comet is C2 depleted, as many other comets from the solar system. Here we can see a statistic. And its spectrum is similar to D-type asteroids. D-type asteroids show a featureless spectrum with no obvious emission or absorption bands. And D-type asteroids are considered the most pristine class of asteroids and are composed of organic silicates and carbonaceous chondrites. And we can say the same thing about Borisov, that is one of the most pristine comets that was observed. Further, within the context of many different random observations using different telescopes and approaches, we propose another way of observing the comet constantly during a longer period of time. And to fulfill this, we took advantage of TCS, the Carlos Sánchez telescope, and its capabilities to observe and monitor the comet by performing multi-band photometry. In addition, we acquired the data with the INT telescope, the Isaac Newton telescope, in BVR and I filters, and we use this data more to cross-check with the TCS data. The purpose of this constant monitoring is to characterize the photometry of the comet by determining its color indices, the scattering cross-sections, and these quantities can be further used to estimate dust production rates using an appropriate model. So we implemented a model that is focusing on the dust grains that are present in the coma, and not on the tail like the usual models that we mentioned earlier. On the spectroscopic side, we detected the presence of cyan, ammonia, and forbidden oxygen lines, for which we determined the gas production rates using a Hazer model. Now let's briefly describe the instruments. Most of the data is coming from TCS. The Carlos Sánchez telescope is equipped with Muscat 2, which is an instrument that can do simultaneously multi-band photometry. Here we have an image. Here one is the cascade focus, and here we have the 4 filters, for which we have here a plot with the transmittance for each band, so G, R, I, and Z. The next instrument, Isaac Newton telescope. Here we have retrieved and processed data for 5 nights of observations, and we use the CCD4 of the wide field camera. This camera doesn't perform simultaneously photometry, but it has a mosaic camera, meaning that in a cycle time of 42 seconds, we can acquire the images consecutively in different spectral bands. The spectrum, we retrieved the spectrum with the William Herschel Telescope. So we use the intermediate dispersion spectrograph and imaging system, which is a high-efficient double-armed spectrum. We can see here some of its characteristics. And however, because of the poor weather conditions, we used only the spectrum retrieved from 27th of November. So the main part of our work consists in the photometry. So our photometric observations with TSC and INT started 2 months before perihelion on 3rd October 2019 and ended a few days after the perihelion passage. For TCS, we analyzed the data acquired in 23 different nights, each night consisting in between 1 to 2 hours of observations. A summary of the observations can be seen here in R band. So for each night, we summarize the observation with 1 image that is obtained by combining all of the exposures that were taken that night. By combining them, we can increase the signal-to-noise ratio and get better quality. And the atmospheric conditions and signal-to-noise ratio vary between nights. So because of that, we may have varied uncertainties. How we process the data and obtain those images by following the 4 steps described here. So first, we apply the usual bias, dark and flat corrections. We remove the sky background. So we subtract the median value of the sky and remove the contribution to retrieve the cometary profile. We calibrate it, and we use the photometry pipeline software to determine the 0 points. And we had 2 types of calibration. The usual ones, astrometric with the Gaia data release 2 data, and the photometric with using the Pan-STARRS catalogs. Finally, we extract the profile, and we had 2 different methods with GeoAstro and with AstroPy in the case of 15,000 kilometers aperture. After the data reduction, we may start determining the physical quantities of interest, and I present some of them here. So the apparent magnitudes, each magnitude in each different filter uses a different 0 point. So after the calibration, for each band, we'll have a different 0 point. And it's the logarithmic representation of the flux in that band. And the absolute magnitudes are absolute in the solar system, so each observer in the solar system will see the comet having the same absolute magnitude. And the effective scattering cross-section, that is related to the reflectance. So basically with this quantity, we estimate the total surface that scatters the light towards us. And we take into account also the solar flux. So by this subtraction, we are removing the contribution from the sun, so we can focus solely on the contribution of the comet. Other two important quantities, the dust production rate, so the number of dust particles produced per unit time. We can express it also as a mass rate, so the mass loss of the nucleus. And when the mass of ejected dust exceeds the newly produced mass from the nucleus, we can compute a net mass loss, which is the difference between the produced one and the ejected one. And with these quantities, we can monitorize the total mass of dust in the coma, the total ejected mass, and how active is the comet. If it produces more dust, then there will be no net mass loss, and the mass in the coma will increase. And finally, to compute this, we use the model. So we use the framework proposed by Fink and Rubin in 2012. And this is based on three assumptions. The outflow velocity is constant for dust particles of same size. The outflow is spherically symmetric, and there is no production or destruction inside the coma. And they propose this size distribution formula. So it's based on an exponential and a power law. And here we have some free parameters and the normalization constant that we will determine. This distribution works like a probability density function when we want to compute global physical quantities for the entire coma. And so we assume that we have constant outflow velocity for the particles with the same size. And Monte Carlo simulations show that the size dependence is given by the inverse square root. And we can notice in this figure that at different distances from the nucleus, we have different velocities. However, it is accelerated fast by the gas molecules, and at 20 kilometers, we reach a terminal speed that was determined from the simulation that respects this law. Later, we will see that we also determine this so a brief explaining of the calculations that allows us to compute the global quantities. The velocity distribution of the outflow velocity is spherical and symmetrical, so we can take an interval of time, here delta t, and we can write the total number of dust particles that are produced and the volume on which they are spreading, so we can calculate the density of particles. Then we compute the dust grain density on an entire column, and we integrate over all the columns to find the total number of particles. After that, we can apply the dust size distribution, and we can find the density of particles with a specific size A. And integrating over all of the sizes, we can find the total number of particles in the coma. Similarly, we can switch to mass and obtain the mass of all the particles with size A, the distribution, and the total mass. If we want to derive the rate of the dust production, we simply differentiate with respect to the size, and then we integrate using the same size distribution. And here we obtain the mass loss of the cometary nucleus. Okay, so the first result we obtain is the morphology. And let's characterize the cometary profile. We obtain for one of the nights here the image. We can see clearly from the image that is a diffuse object. We compared it with some apertures, and chose the 15,000 kilometers one to compute the color indices. So we'll have a fixed aperture for each night and monitorize these color indices. If we plot the normalized surface brightness and compare it with the reference stars, we can see once again that it's a diffuse object, of course. And here the reference stars profile is actually given by the SIM, so it's depends on the atmospheric conditions. On a good night, we'll have a narrower profile for the reference stars. And okay, this profile is obtained by simply taking consecutive apertures. However, we can extract the full profile by using GeoAstro, and we use the ASNOISE TCL tool. So this tool is giving us the full profile, so the full tail extension, by going determining the limit between the signal and noise. And we obtain this mask that we are applying on our image, and by doing this, we are retrieving the total profile. This can help us when we are determining the length of the tail, or if we want to characterize the tail of the comet. For instance, here on 2nd November, we determined the length of the tail, actually a lower limit for the length of the tail of 40 terrestrial radii. If we want to analyze the profile in detail, we can plot the surface brightness expressed in magnitudes with respect to the aperture length. So we can observe here two parts. The first line corresponds to the coma, while the second is steeper and describes the tail brightness until it overlaps with the noise. So here we have the overlapping with the noise. And we can see here knee. So we used two linear fits to fit this distribution. And the distance to the knee is actually the coma length field. So this gives us an estimation about how large is the coma. On the figure, we can see the profiles of all four filters. And one thing we can notice is that there are no morphological differences between filters. So this indicates that we have a homogeneous composition in the coma and also in the tail. Well, after determining the coma length scales, the coma extension is actually limited because of the radiation pressure. So the pressure increases with the distance to the sun. And because of that, the coma size is decreasing as well when the comet is closer to the sun. There is a linear relationship. We can see in this equation that there is a linear relationship between the coma length scale, is denoted with x. So between the coma length scale and the squared heliocentric distance. And from this relation, we can determine the terminal speed of dust grains. And a linear fit here in the plot, from this linear fit, we can estimate the velocity. And our estimation was very close to the results coming from the simulations. So we can say that we validated the results, the simulated ones. And this result is important because we will use it later to compute the dust particles distributions and mass. Let's analyze the photometry and spectro-photometric properties. So we'll do this in each filter and see if there are any interesting trends. First, we retrieved the light curves. So Nothing unusual here. The magnitude is increasing with respect to time. And for one night, we'll have this kind of light curves. Here we can see some smaller fluctuation due to atmospheric effects. And after retrieving the magnitudes for each night, we can compute the color indices to have an idea about the spectrum of the comet. Here we can see that from the values, we can see directly that the comet is a red one. So, and we can see that they are clusterized around an average value. Of course, there are some outliers due to the larger uncertainties. For some of the nights, we had a fewer exposures, so the uncertainties were a bit larger then. The average values we got are alike with the ones reported by other groups. And we can see that with respect to the sun, the comet is shifting the spectrum towards the red region. So, and compared with the active comets from the solar system and the trans-Neptunian objects, we can see a similarity. We can say that it matches with the both groups of objects. Another important parameter, we can observe here the scattering cross-section with respect to time. And we compare the values that we obtained with other values reported by Jewett and Aravind. We can observe a clear trend. Here at the beginning of October, we see a mini outburst that can be correlated to the crossing of water ice line. So the comet started to produce the water gas particles. However, this increasing trend is not sustained. So because of the lack of water, the comet had a small increase in activity, and after that went in a normal level. So this constant trend here can mean that there weren't any increase in activity and there was equilibrium between the ejected particles and the produced ones. When it approached perihelion, you can see that the trend is decreasing. And this means that the ejected mass was larger than the produced one. So the activity was starting to decrease as well. If we get all the cross-section and normalize it to one of the values, we can see the trend more clear. So another particularity that is not so obvious, but we had the idea that there were other mini outbursts here and here, and we may have a periodicity. But however, these fluctuations are very small, so we cannot, we are not sure 100%. Okay, after we calculated the cross-sections, we can apply the mean scattering theory and the model described earlier to estimate the dust mass loss. And we have here for one scatter the effective scattering cross-section. And we can see that for each size, we'll have a different scattering efficiency. The scattering efficiency is given by the mean scattering theory, and it depends on the wavelength and on the refractive index of the material. And we can compute it for the entire coma using the distribution given by the model proposed by Rubin and Fink. So we tried different size distribution and different materials. Here we can see the efficiency plotted for each band. And we can see the fact that it behaves a bit different in each band. There is a shift between the bands. So this is why we have different cross sections and different fluxes in each band. Here we have the scattering cross section with respect to the size. And trying different size distributions and different materials, we are trying to reproduce the spectrum. So the spectrum of the scattering cross-section is given by this plot. And we tried 3 different materials with 3 different refractive indices. And for each one, different size distributions. We'll plot here the best results we obtained. We see that for pyroxene, we'll have the best match. So further, we used pyroxene to compute these quantities. And you obtain the mass production between 3 and 4 kilograms per second. So before perihelion, we had 4 kilograms per second, and after it started to decrease until it reached a value around 3. The dust production behaved similar, and the ejection speed estimated for the most probable size particles was around 300 meters per second. And after perihelion, because the ejected mass exceeded the produced one, we have a mass loss, so an overall mass loss over the coma of minus 0.6 kilograms per second. And here we have the total mass of dust before perihelion. Further, I will start introducing the spectroscopic result. So both the photometric and spectral results are focusing on the spectrum, and from the both results we can see the similarity with the solar system comets. And here I will we can see a plot of the spectrum retrieved on the 27th on the night of 26 to 27 November. This plot was obtained by combining 4 exposures. And there were 3 solar analogs acquired to calibrate and compare this plot at this spectrum. And the pre-processing steps were the following. We extracted the spectrum inside a specific aperture. We calibrated it using existing known data. And we used the lamp that is shown here. So for each pixel, we meshed it with a wavelength using this calibration lamp. For the flux calibration, we used the reference flux from the previous observations with the TCS. And after the calibration, we corrected the atmospheric extinctions because it's wavelength dependent. And to determine the reflectance spectrum of the comet, we removed the solar spectrum. After removing the solar spectrum, we can also remove the continuum dust spectrum to see the fluorescence spectrum. So to observe the emissions coming from several bands. And here we have the calibrated spectrum. We can see the consistency with the TCS spectrum. Anyway, the TCS spectrum cannot offer us more insights about the lines or local variations. So this is why a spectrum is necessary. And after retrieving this spectrum, we subtracted the dust continuum, and we detected several bands. So cyano, forbidden oxygen lines, and ammonia. And for these bands, we can compute the gas production rate. And we use the Hazer model, the usual procedure for doing this. So we can determine the flux in a certain fluorescence band. And we use a G factor that is known. We retrieve it from the literature. And considering the spherical distribution of the comet, the Hazer model is practically counting all the parent molecules and daughter molecules that follow an exponential distribution. Here there are the values for the cyan and ammonia, and we acknowledge the use of the Hazer model implementation provided by the Lowell Manor Planet Services. Now that we know how to do it, we'll present the results. And the first is the cyan line. We numerically integrate the flux under the spectrum of the cyan line, and we apply the Hazer model. So this was our estimation. We did the same thing for the ammonia. Here we have a little problem that we can see two lines at 6 to 8 here, the first one, and 633 here. Here above we have a standard spectrum retrieved with the Hubble Space Telescope for the Halley Comet, and we see the same bands. However, due to our resolution, we couldn't distinguish between these two bands. And 633 here we have an overlapping. And from this line, we can just estimate an upper limit. Now these are the values. Yeah, for 6 to 8, we successfully determined the gas production rate. Now the forbidden oxygen lines, here we can see them clearly. However, due to Doppler effect, the telluric lines are shifted with 0.4 angstrom. Our resolution was about 1 angstrom, so we couldn't separate them. And because of that, we didn't have any estimations. And also, we couldn't detect the green line because it was out of the scope of the instrument. So we can see here the spectrum with the blue arm and the red arm of the spectrograph. And the green line would be somewhere here, so in between them. The green line would be important if we want to find the abundance of carbon oxide. Now I will conclude. So we have clear signs of activity, a coma length scale extending between 8,000 and 13,000 kilometers, homogeneity in morphology across all the TCS bands. From the photometry, we determined that the coma is towards the red spectrum, so it's similar to the active comets from our solar system. And that also can mean that other planetary systems exhibit similar formation processes. So we computed the dust production rates, and we find that the best match would be with a spectrum of pyroxene with dust grains around 200 to 150 nanometers. So compared to the tail models, we obtained indeed smaller particles in the coma. And the ejection speed around 300 meters, which is larger for compared to the grains from the tail. So because it's larger, it can escape easier from the tail. And in tail, we can't find these smaller dust particles. And from the spectroscopy, we detected the three lines, cyan, ammonia, and the forbidden oxygen lines, and we retrieved a gas production rate ratio between cyan and ammonia of -0.2. So with this, I conclude my presentation. I'll be glad to answer some questions.
Okay, thank you very much. So, is there any questions? Well, while people are thinking, one question I had at the start when you showed the HST image of this comet, it looked like a contour. It looked like it had contours. What is that, the raw image or the
Here?
or no, not this one before. The first HST image you showed at the
This
start.
one?
It was the no, very early in the talk. Yes. What are these?
Oh, this one.
Yeah, contours. Well,
Yep.
why does it look like a contour? Is this a subtraction image? Can you explain this image? Okay. I'm curious.
Okay, this image is from Mancini et al. I don't know how the processing was done. Yeah, indeed, there are some contours. So probably it shows the difference in intensity in the tail. So this is the tail.
Yes.
And here we have the coma, which is more intense.
I think this was a technique that people used to enhance,
Highlight.
to enhance the structure in cometary tails.
The visualization, right?
Yeah, I think it was like a subtraction, but with a slight shift in size. So the radial structure is shown. There's another technique where there's a subtraction with a different shift in angle to highlight the linear structure in the tail. So this should be like a radial, tiny shift in radial size and subtract so you can see this.
Oh, that's interesting. Okay. Yes, Alessandro?
Thanks for the nice presentation. I have
You're welcome.
actually two questions. The first one, you shown the various color indices that you get of the different observations with the TCS. I wonder, and you showed them the average of those. That's right, this one.
Yes, this one.
If you were to plot these color indices with time, would you see any evolution, or would it be just some scatter?
It would be a constant, like a horizontal line. So there are no variation, like obvious variations in time.
Okay. So my other question is, so basically this is the second interstellar object that we know of. What have we learned from this specific one? Can we make a leap of faith and say, because of this, we know that this galaxy was formed in an environment which was similar to other comets in the solar system? Can we do any speculation?
Well, the most interesting fact that was obtained is the lack of water. And because it's a pristine object, so it didn't interact with any solar system, we saw that there is an abundance of carbon monoxide instead of water that led to the presence of oxygen in tail and coma. In particular, the comet was is very similar to the solar system ones. So this would mean that the comets are forming in a similar way in other systems, in other planetary systems. Yeah, and compared to the asteroid Oumuamua, we had also the gas we could analyze. For the asteroid, we only had some reflectance spectra. And I think comets are more interesting because of that. And they are providing with more information.
So following up on Alessandro's question about the evolution in these color indices, did you actually did you actually draw the plot, or is this just a guess that it will remain constant?
Yes, we draw the plot.
Okay.
I think I have some.
Yeah, because well, if it's constant, it shows that the inner structure of the comet, the inner structure doesn't is the same, right? Because as material is going out, we will expect you will expect like if it was a layered structure.
Actually, it could be very interesting if you see some variation in the color indexes in the 3-4 months that it was passing by.
Oh, because when it's closest to the sun is the time that it emits most of its yes, right, it's outer layers, right? So can you like how just as a curiosity to put in a physical scale for me as a non solar system person, how much like for this comet and this mass loss rate, how many meters of the surface have been lost while it passed closest to the sun? Roughly, do you think? I mean, can it give any like any hint on the inner structure of the comet, or is it too small to be significant?
I would be super guessing.
Well, we can basically so we want to calculate the number of particles that were ejected.
Yes, the mass loss of about 40 per second, and then.
So the total mass of dust that was in space before perihelion was the order of 10 to the power of 6 kilograms.
Oh, by the way, so those color indices were for the total comet, right? Not as a function of distance.
That's one of my questions. If you have the different color indexes or maybe spectra for the tail and for the nucleus of the comet. I'm not sure if you showed it. Do you have a different spectra for different parts of the comet? So if you try to
all of the results were taken in a fixed aperture.
No.
In a fixed aperture, you mean so for example, like along the length of the comet or in the nucleus, did you try to get different measurements just to see if like as a function of, because distance means time, right? Time from ejection.
We have also the profiles here. Yeah. Here. So this is the flux with the distance from the nucleus.
Yes.
So basically make the difference.
Maybe I can add.
the same trend for each band.
Maybe I can add something regarding these questions. Yes, we tried to plot overall it's homogeneous. We didn't, at the level of our detection limits, we didn't find any inhomogeneities, any heterogeneity between different parts of the coma or with respect to the solar system heliocentric distance over time evolution.
Okay.
If there are any, those are below our detection limit with the Carlos Sánchez telescope.
Okay, thank you.
Thank you, Marcel.
Any more questions?
More questions from remote audience? No.
Okay. So if there's no more questions, then I can like to thank George again and Marcel.
Thank you.
I would only like to add that George did a tremendous work. He started from zero, basically, and he worked a lot to process the observations coming from different telescopes, from Carlos Sanchez, from Isaac Newton, from William Herschel, and I think the results are nicely complement the one that are already available in the literature, because being an object of such interest, there are many researchers that followed it with various telescopes, various instruments, different levels. Our specific result was this observing campaign and to monitor its behavior before the pre-perihelion passage.
I have last question. Sorry.
Go ahead, David.
But I would like to know if there is some way to estimate, knowing the orbit, the composition, and whatever, to estimate how long has this thing been traveling through our galaxy. There's some kind of way to do a crazy estimation, or not?
Well, at least you can start. The comet was active, so definitely, if this object passed near a star, it loses some material at every close approach to a star, depending how close it goes through a star. We had Oumuamua, who was not active anymore and seems to have a spectra similar with the tail. Maybe it has a longer history compared with this comet. Otherwise, what you can do, you can also compare its speed to see from how far it's coming. If the speed is similar with the stars that are nearby, or it's come from farther away, that will means a larger speed depending on the geometry. So overall, I will say we don't have clear clues, but the fact that we have an active comet, it gives us the information that it didn't pass it very close by to other stars.
Okay. Thank you.
Okay, well, thanks again. Thanks again, everyone, for coming, and hope to see you soon.
Thanks a lot for inviting.
Thank you, George.
Thank you for your invitation.
You're welcome.
Ciao. Un año, Va a tener que traer. De hecho.
Okay. Bye-bye.
Goodbye.
Bye-bye.
Bye-bye.
Yeah.
Aparte, sabiendo que